about the XR3 hybrid. So let's take our time to give Bob a nice welcome and enjoy his presentation.
Thank you, Josh. I'm hearing some feedback, and let me see if I can find the dial. You know, I sent out a note to some folks who purchased plans, and I know some of the folks did come, and I'd just like to know, you know, by hands, how many people are here who bought XR3? I mean, then I couldn't do it now without people who supported me in that way, because, you know, like, I'm not a wealthy guy, and so I need income to do this kind of creative work, and you guys are supporting that, and I appreciate it. Thank you. So the first slide is the recently completed prototype of the XR3, and you know, my money, my time. I'm the main design guy, and. But I would like to just briefly have some people stand up that were part of the team, and I'll acknowledge it a little bit more later, but there's one person in the team that's not here. He's got a better job in California. But Galia, my wife, and Bill Beckner. Bill Beckner was the lead guy in the prototype department. You guys all know Melissa is the person who writes the SAE newsletter. I get the credit for it, and she does the work. So that's how it works. But the XR3 is a parallel plug-in hybrid. It can operate on battery power only, on diesel power only, or on a combination of the two. It has a 40-mile range on battery power. It gets 125 miles per gallon on diesel. It'll do 75, 80 mile per hour top speed, 2 passengers side by side. And so tonight I'm going to talk a little bit about the technical part of the XR3, and I'm going to give you a little background. Can I have my glasses there? You know, I hate bifocals, and I end up doing something like this. And people say, "You mean you really hate bifocals? What are you doing?" So, I have a choice, see far or see close. And can I have the next slide? Yeah, there you go. And this is sort of the background, you know, to give you an idea. Those of you who know me know that I've, for lack of a better word, I've always been into so-called alternative car design. And I really started Urbacar in 1974. Thank you. I need a good engineer. A little 650-pound car, 60 mile per gallon, 60 mile per hour. This was a street legal go-kart. That's what it was. 1974. First car I ever designed. It was on the cover of Mechanics Illustrated in 1974. The next one was Urba Electric. And that ran with a constant speed motor, and we used the transmission to control the speed of the vehicle from start up to 60 miles per hour. We didn't bother to control the motor. We only controlled the shift position. Trimuter, 1980, Mechanics Illustrated, 850-pound car, 55 mile per gallon, 65 mile per hour. And then Tri-Magnum, this is still a very popular plan project today. This was a really hot vehicle. The last one that we did in that Mechanics Illustrated series, we thought, well, okay, this kind of time we're going to do a hot vehicle. And it had a whole motorcycle in the back of it and used a VW front suspension. And we drove this car to 100 miles an hour, afraid to go any faster. But, you know, I'm talking on streets north of Phoenix here. But this was a really neat car. But these are the kinds of cars that we did in the 70s and 80s. And they were all featured in either Popular Mechanics or Mechanics Illustrated. And, you know, the first Urbacar started really a series of do-it-yourself cars. And what we tried to do, former company Quincy Lynn, is we never built a car just to build a car. We tried to make some sort of design statement when we built a car. And so that's what we did. For 10 years, we did this kind of thing, and we supported it by selling plants. So it was a great period of my life. And next slide, please. Now, in the second edition of my book, Alternative Cars, there's a line drawing of this concept that's a kind of a theme drawing for the section of the chapter on three-wheel vehicles. But the XR3 really started life as this. This was the original concept. And you can see the date here, 1998. Well, that's when I published it somewhere, and I had to put a copyright date. But this rendering was actually hanging around for a few years before that. And what I envisioned was a tilting suspension, single occupant car. I had been working with some guys at Atlanta Gas Light. They were doing some natural gas storage on carbon beds that was really, it seemed like they were actually on the verge of making some breakthrough. And this little element here is supposed to be a compressed natural gas cylinder. But what the guys at Atlanta Gas Light were researching is storing compressed natural gas on a carbon bed at very low pressures, like 500 psi, which means you could have a two-stage compressor in your garage and you could fill up your car with natural gas, instead of having a four-stage compressor and running at 3,600 psi. You could get as much compressed gas at 500 psi with a carbon bed, in the cylinder, in the storage vessel, as you could at 3,000 psi without the carbon. Amazing, amazing technology. I don't know why it never went anywhere, but at any rate, this was a car that was sort of on the drawing boards and in my mind for a long time. And when I finally got around to prototyping the car, like I'm going to get serious about building this car, this XR3. I never thought there was much market for a single-place car, and so it had to be a two-passenger car. And I backed away from the tilting suspension, because that's a whole job in itself to do a tilting suspension. And I was on a tilting suspension project in the mid-90s, and what it taught me was that this is not the kind of suspension that I want to get involved in designing. It's really neat when everything works right, when the vehicle stays planted, but when the vehicle loses traction, everything, goes downhill quick. And consider, one of the big things, consider that you're leaning to the inside of a turn, right? And you lose traction and you spin out, and now you rotate 180 degrees. Now, where are you leaning? You're leaning to the outside of the turn, right? Bad news, you do not want to lean to the outside of a turn. And correcting that while you're spinning would further upset the vehicle. So I know there's that bend and brink carver in Europe, and they've done a pretty good job on solving these issues. But I was so afraid of it, I said, what am I doing? I know how to design a three-wheel car that has a 1.2 G rollover threshold, and so why do I need tilting suspension? It's a whole development issue of its own. Now, I'll show you a couple of styling things that I did with the XR3. I came along with the bottom of the car, and I covered up the drivetrain and the wheel in the back, and I covered up the bottom of the passenger zone. What I have is a very fat body, and that doesn't look good to me. So I said, well, okay, I'm just going to bring the body up. Well, when I brought the body up, I saw the passenger zone hanging down right here and a bunch of hardware. So, I had to have a way to hide it. So I put some stuff on here originally in the model. And I didn't know what that stuff was for, but I just put it in there to hide, as a styling element. Another problem I had was the engine was too tall and it stuck through the hood. And after 3 months of trying to restyle that hood so that I could cover the engine, I decided, well, I'm just going to let it stick through. And that's why this element is on the hood. The engine sticks through the hood. And so I covered it with a kind of a hot-looking plenum chamber. Like if you open the hood of a modern car, what do you see is this real cool-looking thing, you know, that covers the, it's a plenum chamber, air intake. And so it's kind of a blower-looking, kind of suggestive thing. So that's what that's for. It's because the engine sticks through the hood. So anyway, that's the styling that and when I start on a vehicle design, one of the first things I do is I decide on general packaging, and then I do the styling. And styling, you know, some folks think, well, maybe that's like the afterthought, the thing that should come later after the car works. Well, for me, that's what comes first, because I want to see something that I can feel excited about. You know, kind of a visual marker that I'm working towards. So the first thing I do is style the car. And I only have a general idea of what's going on inside here. But I knew we were going to run a rear wheel with a motor, and we're going to run an electric motor, and we're going to run the front wheel with a, an IC engine. And I knew we were going to do diesel so we could get super high fuel economy. So I knew those things. And I knew I had to have space for them. So there you go. That's the styling. Next slide. Okay, now one of the things I did with the chassis, and I really did too good of a job for a build-it-yourself project. And what I did, well, first of all, from the build-it-yourself angle, see, what we have is a front subassembly, a rear subassembly, and then a backbone that connects the two together. Now, this front subassembly carries the entire IC drive package. The steering, the suspension, the transmission, the engine is integral to this part. The electric drive package is integral to this part, and it bolts to the tunnel. Now, that turned out to be quite an engineering job to make sure that I was doing things right. And Bill kept coming in asking me for drawings, and I kept saying, wait a minute, Bill, I haven't finished designing this thing. So we were building and designing at the same time. But the idea is, and the other basic concept is that the drive package, this IC system, and this electric system are not connected within the vehicle. You know, and what caused me to do that is that when you connect the two systems together, you need to integrate them in some way. You need to computer control them in some way. And so what I said to myself, well, I'm going to set hybrid technology back about 25 years, and we're not going to even integrate them. We're not going to worry about it. And all we're going to do is we're going to integrate them with a simple, what I call a mode selector throttle integrator. And I'll show you a little bit about that later. 5 mile per gallon car. Or, you don't need all this IC stuff. You just disconnect it at the wheels. The wheels are self-supporting. You can put extra batteries in here, and you can have a 100-mile range electric car. Or, you could put in a hot engine up here. This is only a 23 horsepower engine. You could put in way more horsepower, and you don't have to balance that out to the electric system, because you're not integrating them anyway in the vehicle. So you can do whatever you want to with either of these systems, and you still have two systems that will work together. Now, to me that sounded almost too simple, and I kept looking for the gotchas in this. And I'm telling you, the car works so beautiful. Even when my throttle integrator is out of adjustment, it still works. And so I'm really, I'm happy. I'm happy. The other day, Bill came back from driving, and he got out of the car, and I said, and I came in the garage, and he was limping, and I said, what happened? And he says, I'm so happy that I started jumping up and down, I threw my back out. He said, this car's beautiful. So, the IC and the electric system are not integrated within the vehicle. They are tied together by the ground. So, next slide, please. I might try something here. See this little icon over here? That'll launch an e-drawing. And oh, wait a minute! Don't click anything. I'm deciding whether I'm going to take a chance. But this is the entire IC drive system. You can see the half shafts going on, the transmission. We've even got the shifter floating in midair. The shifter is actually bolted to the body. And you know, there's your stabilizer bar, your lower controller. the suspension at all 3 points is controlled by an air spring. Now, air springs ride nice, right? They're known for beautiful ride. But the reason I put in air springs is because I'm thinking about it. Some people are going to outfit this car differently, and even if it goes on into a production level, customers may want to outfit it differently. Well, how do we count for the different weights of these vehicles? Well, all we do is put more or less air pressure in those air springs. And we don't have to have different springs spec'd out. I mean, it's just a beautiful solution to that problem of center of gravity and weight. And I'm not going to launch this one. This one is a big file, and I'm afraid that it won't be worth it. Okay, I'll launch the next one. So let's go on to the next slide. This shows the real car with the front end removed. Now the whole front clip comes off of this, the front of the car, like what you see there. The front clip is tied in with rubber dampers here and here to the passenger zone. That's the only place it's tied in. The rest of the front clip is bolted rigidly to the front assembly. And the front assembly is mounted to the tunnel with vibration dampers. So what we're doing is we're saying is we'll let that front clip vibrate, with the engine and, the stuff that's going on, IC stuff. And we just want to isolate the vibrations from the cabin. And so, and this provides beautiful access. It takes about 15 minutes, right, Bill? 15 minutes? To take the whole front of the car off. There's one electrical connector, and then there's, 6 or 7 bolts, right, or 8 bolts?
Well, 6 right now.
6?
Yeah.
You mean you left off some bolts?
Yeah, we decided we didn't need the other 2, so.
Okay. Okay. So anyway, 10, 15 minutes, the whole front end of the car comes off, and that's what you see. And, total access. Total access. Next slide. Okay. I think I'm going to play with my little e-drawing and see how it works. Okay? Yeah, just click that. Yeah. Dun-dun-dun-dun. Let's see how it goes. Is it launching? Is nothing happening? There it goes, there it goes.
File erased.
Now what I want to do is get, okay, I'm going to do this. Yeah, this is really cool stuff. I love this technology. SolidWorks, 3D modeling, e-drawings, and all that sort of thing. That is the tunnel. There's 2 batteries in there, there's a fuel tank in there, and it's basically a rectangular steel frame that's covered by sheet metal. That whole tunnel could actually be built out of drawn metal parts, sheet metal parts. If it was built properly, it doesn't really need all that structure in there. For building one off, we put structure in there. But that's the tunnel. I mean, and the body bolts to this. The body bolts to this. The body does not bolt to the front assembly or to the rear assembly. It bolts to this. So, and I want to show you what how the vibration dampers are made. Can you guys see that? Yeah. Now you're going to say, oh, okay, so big deal, right? But that's the vibration dampers, and that's at 4 places in the front and 4 places in the rear of the tunnel. Now you know what I did? Oh no, I didn't. There we go. I thought I closed out my slide, my PowerPoint. Okay. So that was pretty cool, wasn't it? I love this stuff. I'm 68 years old. And I didn't get into 3D modeling until like maybe 8 years ago. And it's like, for me, it's like playing, you know, it's computer games. And I just love it. I love the technology. I know people my age that say, I won't touch a computer. Well, I'm a computer geek. I love it. This is the rear drive package. It's totally integrated drive package. This is the electric drive and the suspension system. And I'm probably going to launch an e-drawing here too. So you can see what, you know, there's an air spring. Up here. And again, the inflation pressure really accounts for any CG difference if you've outfitted your car different or what have, or if you've left the electric drive out of the system. The inflation pressure that you put in here accounts for that difference. And it mounts just like at the front of the tunnel, 4 places with these urethane vibration dampers. This is a 2-stage timing belt drive, and there's a clutch right over here that actually takes the motor out of the system. So when you're running on IC power, you're not having to spin up that armature of the DC motor to accelerate. So the armature, the motor, is taken out of the system when you're just doing diesel only. And you know, it's very simple. Why don't you launch that e-drawing and let's play that and see what I can show. Yeah, okay. Now, one of the things about this drive package is we're using the motor itself as a structural element of the drive. And if that motor's not in there, that housing is not strong enough to carry all the yanking around of the rear wheel. So if you built that rear assembly and left the motor out, like you weren't electrifying it, you need to add like a 6-inch diameter pipe to add the rigidity back into that housing, because the housing will not carry the wheel without that motor in there. And so I think I can show you how tightly this is packaged. Okay, so what I've done is I've made that transparent. So you can see that the wheel pivots around this point here, and then the motor's right here. It's only about that far away. So the swing axis of the rear suspension is very close to the motor. And really, that's what gives it the strength, the motor itself. So, okay, let me close this. And I'll close the presentation. There we go. This is working pretty cool. Okay, next slide, please. Now, that's what it looks like in the real car. See, there's the drive package, and there it is mounted in the car, and the trailing arm. And would you launch that e-drawing right there? This is the integrator mode control. This is probably the most, for me, the most clever thing in the whole car. And the car that I had, and the thing that I had nightmares about until I tried it. Like, I didn't know if this was going to work. You know, I mean, maybe there's a reason they put complex computer controls in hybrids. And maybe I'm just too stupid to understand it. You know what I'm saying? And it worked. Let me stop this. I want to show you something. Okay, I'm going to do, okay, and I'm going to stop it right here. Okay. This would be in the hybrid or the IC only mode. Now this little, you know, this position, okay, this position. This is the throttle integrator. Now the throttle from the cabin pulls at that hole, pulls this lever back. Right here there's a spring that goes up to pull the throttle on the diesel engine. And this little box right here is a pot, you know, a rotary pot that tells the electronic controller how fast, how much current to put to the motor. So when you pull this lever back, then more power goes to the motor. Now, so what we've done is in this position, you see that little head on that nail? Well, when this throttle lever moves back, it doesn't move this pot until the head of the nail gets back to here. So what that does is it gives you a delay. When you step down on the throttle, you're actually throttling the diesel engine. And the electric motor doesn't throttle up until this part gets back to this part. Now, the lags, you know, where you want the electric motor to pick up is entirely adjustable. I mean, everything in this is adjustable. So, you know, it's adjustable to driver preference. Do you want to kick in that motor right away and, you know, really boost the car right from the start? Or do you want to drive conservatively and drive on diesel as much as you can, and only when you really want to nail it, when you got it, you know, you have to get out of the way of something, then you go ahead and floor it and you dump in the power from that motor. Now the difference that makes, consider that you're running on 23 horsepower diesel engine, right? And the motor itself will deliver about 50 horsepower. So you go from a 23 horsepower car to a 50 horsepower car virtually instantly by mashing down on the throttle. That makes a huge difference in acceleration, as you can imagine, you know, like 3 times more power, right? And, but if you are driving conservatively and you don't need that power, then you're driving at 125 miles per gallon. And what you are doing is carrying your burst power along, your acceleration, your quick acceleration power, from your wall plug. You know, that's wall plug energy. Now, if you had to carry that power in your engine, like by having a bigger engine so that you have more throttleability on the engine, now what that does is put you in a situation where you're always running this big engine throttled way back to maybe 5 or 10% of its maximum output. So you're running way outside its lowest BSFC, right? So you want to get that engine up into at least close to its lowest brake specific fuel consumption point. Engineer said. You want to get it where it's putting out, where it's using the least fuel per unit of power output, is what you want to do. And an engine doesn't do that when it's throttled down to like 5 or 10% of its maximum output. Burns a lot more fuel for the amount of power. You know, like 150 horsepower that's putting out 8 horsepower is a terribly inefficient engine. 150 horsepower engine that's putting out 8 horsepower. And when you're cruising along at 40 miles an hour, you're cruising along at 8 horsepower output, roughly. Right, Howard? I mean, nothing. You're not using any capability of that engine at all. What the rest of the engine is there for is for when you need the acceleration. Now, if you carry that acceleration around in an electric motor, then you don't have to carry it around in an engine and run it for very inefficiently for most of the time. So that's what that boost is all about, is you take that acceleration power from your home, from your wall plug. So that's the hybrid and the IC only. And then I allow this to play all the way out. That's the battery only mode. As soon as you press on the throttle, you're operating that PB6 control, and instantly you have electric power going to your motor. I hope I'm not getting too... I'm speaking to engineers. This is not too technical for engineers, huh? Engineers love this stuff? Right? Tell me somebody loves it, right?
I love it.
Huh? I love it?
Very good.
Okay, so yeah, next slide. Now, I'm going to show you step 1, step 2, step 3. And this is where most of the labor of the car is, right here. And I'm going to tell you can build a body in 3 simple steps, right, Bill? First, you build a foam body. Then you put fiberglass on it. And then you sand until smooth. And you know, in the early plans, we used to say, when we got to this stage, sand until smooth. And my partner and I used to laugh and say, well, that's about 3 months worth of sand until smooth, right? But this is where the work is, and getting the body ready for paint, you know? And this stuff is really kind of fun. It goes quick. You know, you get from nothing to like a beautiful car real quickly, and then you put fiberglass on it and make it ugly. So it goes from a really pretty foam body. It gets a lot prettier than this. It starts looking like a real car very quickly after this. And then you fiberglass it, and then it gets uglier and uglier, and then it starts becoming pretty again. Well, to me, this is pretty because it's almost ready for paint. But once you shoot that with primer, and I mean, you end up with what's sitting out there in the parking lot. Beautiful car. And even though I've done this 20 times before, it's hard to imagine that something like this ends up looking like what's sitting out there. You know? I mean, how does that happen? How does it happen, Bill? A lot of work.
I don't think about it anymore.
You know what I think about it? Okay, so next slide, please. I hope I've covered enough of the technical aspects of it to kind of like fill your appetite for what's going on. But, you know, 125 to 225 miles, 40 miles on battery power only. This is Galia, my wife. Stand up, Galia. Let her see this. Do it. This is my beautiful wife. But, and now, you know, I want to really acknowledge the team that was involved in this car. And again, I did at the beginning, but I'd like Melissa to stand up, you know. Melissa is my granddaughter, right? And I sent her to SolidWorks training about 2 years ago. And I said, Melissa, I'm going to pay for your SolidWorks training, and you can work here, and you'll become proficient at SolidWorks. The only thing I ask for you to do is stick with me until the XR3 is done. And she said, okay. So this lady she has enough hours to be certified. She's 20 years old, right? And she is essentially a certified SolidWorks CAD operator. She does the newsletter, she knows Core, she knows HTML. What else do you know?
How to make babies.
How to make me a grandfather.
And so I want you guys to know if anyone wants a super talented, super smart young lady, that Melissa is available. And I don't mean like available as a girlfriend. I mean that her skills are available. So I can't believe that my granddaughter did 90% of the SolidWorks model that went into this car. Huge thing. And Bill Beckner. Yeah, stand up, Bill. Stand up. Bill is also Melissa's father. Okay? And about a year and a half ago, I said, hey, Bill, I'm building this car. Do you want to come and help me? He said, oh, yeah, but I don't know anything about it. And Bill had never fiberglassed before, and I bought a big welder, and he's, wire feed welder. He said, well, I did this once, and he hit the welds. If you saw welds in this car, the welds hold, but they're some ugly welds.
They're still better than yours.
They're better. And anyway, Bill virtually built this car. We had one other prototyping technician that Bill was in charge of, and Bill was mainly cleaning up his messes, but Bill built this car, and he never did this before. So I want to acknowledge him for that, Bill. And my beautiful wife, Galia, she did all the image setting. There's maybe 300 images in the book, and each one of them has to be annotated and put in the right, resolution, and then one resolution for color and another resolution for black and white. Galia did all that grunt work, and then she served sometimes as a model, and I guess I'm prejudiced. I think she looks good, you know what I'm saying? So Galia, thank you for the work. And You know, when things don't work right, I could be really ornery, right? No, that's what I'm saying. So, thank you. Questions? I mean, I'm here for you guys, you know. Yeah.
When the electric motor kicks in 100%, what happens to the diesel?
What happens to the diesel?
Does it disengage? Does it turn on?
No,
Does it go
no, it
back?
doesn't disengage. And you know, one of the things we need is a shift light. And you can actually, you know, if you really punch it, you can, I mean, you get a feel for it, you know when you're overrunning the diesel, but ideally, we should have a shift light. When the diesel reaches 3600 RPM, it should come on and say shift. But we can actually, you know, be pushing it past
So it
the
doesn't go
maximum
into idle
RPM.
mode, it actually just accelerates with the electric motor.
I'm sorry, say again?
The diesel just accelerates with the electric motor.
Yes, it does.
So
In other words,
then
the diesel's putting in its power and the electric motor's putting in its power, but the diesel runs out of RPM at 3600. The electric motor doesn't know and doesn't care, right? So if you're not like paying attention to the feel of the car, you'll actually outrun the diesel. And what we need is a shift light, you know, and we don't have it. Howard?
Bob, is that a liquid cooled engine?
Yes, it is.
Liquid, where's the radiator?
Off to the side there, I think.
We didn't have room for a radiator, Howard, so we only drive it maybe 3 minutes at a time. No, the radiator. The radiator's on the other side, but this is a scoop for the radiator. And originally we intended to have 2 radiators, one on each side.
Yeah.
But that diesel needs so little cooling, and those custom radiators are so expensive. We decided, let's see if we can cool it with 1 radiator. And it cools fine with 1 radiator. And the radiator that was originally sized, the engineer told us we needed 2 of them. We actually have 1 of them. And it cools fine. In fact, these scoops, the inside of these scoops were designed for a smaller radiator, and had they built it smaller, I'd have used 2, and everything would have been real cool. But this radiator is too big for that scoop, you know? And we just stuck it in there anyway and put a fan on it, and it cools fine, you know? But when I got those 2 radiators in, like the engineer, you know, I forget where we bought them, but he did the engineering on it and said, well, here's what you need. We got them in, and I looked at those radiators, and I said, no way, no way. Because I'm familiar with that diesel engine, and I know how little cooling that little 3-cylinder diesel. I used that diesel engine virtually an identical displacement back in 1982 on a car called Centurion. And, you know, in that car, it didn't even have a water pump. It was convection cooling. That's how little cooling. And it scared me. You know, I mean, I just don't trust convection cooling. And we actually put a water pump in the car, and it was always overcooled, you know? So, anyway, we put 1 too big of a radiator on the other side, and it doesn't fit the inlet. And we put a fan on it, and we don't have any problem. So, but that's where it is. It's opposite this, just on the other side of the car.
Do you have any air conditioning in it?
No. No, at 23 horsepower, you turn on the air conditioner, the car stops. Well, a car takes about 5 to 7 horsepower, you know, for air conditioning.
The air conditioning takes 5 minutes.
Well, yeah, the air conditioner, that's what I mean. To cool a car takes about 5 to 7 horsepower. So if you were going to put in an air conditioning system, and there's nothing that says you can't, you know, I mean, all you have to do is drive the compressor, and you know, and put your evaporator and your condenser and blow some air across them, and you have air conditioning. And but you would need to put in a larger engine, or run it with electric power and sacrifice range. But you know, air conditioning is a huge energy sap. So, yes.
Was that an advanced DC motor? Are you running a DC system on the electric?
Yeah, it's a DC system, and it's advanced DC motors. It's their 8-inch motor, is that right, Bill? Their 8-inch motor? Yeah. Yeah, we're running 115 volts, and it's rated up to, I don't know, 144 volts or something like that. Yeah.
If you deleted the motor, just ran on Diesel.
Yeah,
How much weight would you save from the batteries and the motor?
pretty close to 600 pounds. This car is about 1,480 pounds, so it would be down under 1,000 pounds.
So
You
you'd get a lot better mileage, right?
No, not necessarily. You wouldn't really get better mileage, but you'd get better performance on diesel only. You know, and really it's pounds per horsepower translates into acceleration, really, you know, pretty much. But you get a more lively vehicle if you left out the electric, and you would save about $15,000 in building costs. All the costs, you know, I mean, the really expensive items are in electrifying the chassis. You know, there's $9,000 worth of lithium-ion batteries in this prototype, and that's only 6 batteries. You know, I mean, if you put lead-acid batteries in this vehicle, you could put, you know, an equal amount of punch in lead-acid batteries for $1,600 maybe instead of $9,000, but you wouldn't have anywhere near the energy density. You know, your range would go way down. So we put lithium-ion because, well, we wanted the range and we wanted the high-tech, latest, super-duper stuff, you know? But there are other alternatives. Yes?
I've been following the development of the XR3 pretty much from the start, and you initially announced that you were building a vehicle that would have, you know, 125 mile range on diesel, or 125 mile per gallon.
On diesel.
Sorry, 125 miles per gallon on diesel and a 40 mile range and an 85 mile per hour top speed. I presume those numbers a year ago were projections.
That's right. Yeah.
Theoretical.
That's right.
How does the performance of your vehicle compare to your projections?
It compares pretty well. We haven't done top speed. We don't have an e-meter in the car. We need to do that. So we really do need to you know, verify all that stuff. And we will be doing that over the next 2 or 3 months. But when I make the projection of 40 miles range, it's 7.5 kilowatt hour battery, and the car should use about 140 watt hours per mile. And if you calculate that in, you end up with roughly 55 mile range. And what I did is, and right now I don't know what the range is, you know, because we haven't done those tests. And what I did is I backed off on that. You know, I made that real conservative. And I know that we're not going to be using more than 140 watt hours per mile. We're just not going to be doing it. 140 watt hours per mile is what the EV1 used, and that was like 2,500 pound car. And we have less than 1,500 pounds. And so I'm saying, okay, we're going to use 140 watt hours per mile too. You know what I mean? It's like a bunch of fudging. You know, like to be conservative. So I'm not worried about 40 miles. I'm very comfortable with that. And I think we're really going to end up with, you know, 55 mile range at least. But I'm not saying that, okay? I didn't say that. And the 125 mile per gallon, I was going to put a slide in here so I could show it, and I forgot. Actually, that's not been tested yet either. What that's based on is in 1982, we built a vehicle called the Centurion, virtually the identical engine, 4-wheel car, within 300 pounds weight of this car. And we tested it north of Phoenix, 128 miles per gallon, and by using a beaker and running up a grade and then down a grade and then up a grade and then down a grade and averaging the fuel economy. There's no way that this car is not going to break 100 miles per gallon. You know, it's a 3-wheel car. It's, you know, we're not doing anything new. No new technology. Yes?
Now, why did you choose the 3-wheel configuration? Was it for performance? Was it for economy? You know, what was your major?
You know, the major, first of all, I happen to like 3-wheel cars. You know, and I have a lot of experience. I'm just partial to them. But there is a legal issue. A 3-wheel car is classified as a motorcycle. According to the Federal Uniform Vehicle Code, as a legal distinction, three-wheel cars do not exist in the United States. There's no such thing as a three-wheel car. So if it's three wheels, it becomes a motorcycle. Now, once you become a motorcycle, a whole bunch of things get easier to deal with about licensing a car. If it was a four-wheel car, I could not use an industrial engine, at least in California. They have it right in the code that you can't use an industrial engine to power a passenger car. And it doesn't matter if it gets a zillion miles to the gallon, you just can't do it. Doesn't matter if it meets emissions, you just can't do it. You know, it says right in there, it's an industrial engine, you can't do it. So, there really are licensing legal issues, and there's a big loophole right now, and there has been for forever around three-wheel vehicles, that you don't have to meet the standards that you do in a four-wheel, in a four-wheel car, like a real car, right? Now, Canada, about 2 years ago, 3 years ago, wrote regulations for three-wheel full-body vehicles. I think the United States will do that. I think it is out of sync with reality to say that that's a motorcycle. That's not a motorcycle, that's a three-wheel car. And but right now, there's that legal loophole. And now Canada wrote some really nice regulations that didn't place this kind of vehicle in a passenger car category, but got it out of the motorcycle category. And see, there's certain things about motorcycles that, of course you want two headlights. You don't have to have two headlights on a motorcycle, but of course you want two headlights on something like that, you know? You only have to have one stoplight on a motorcycle. Well, there's a lot of things that aren't required on a motorcycle. Seat belts. I mean, imagine a requirement on a motorcycle to have seat belts, right? You want to kill every guy that falls off a motorcycle. But of course this car should have seat belts, And things like that. There's things that don't make sense in the motorcycle category when you apply them to this kind of a vehicle. They don't make sense. They're crazy, Yes.
How about the stability of a three-wheel as opposed to a four-wheel when you're turning, as far as rollover?
Yeah, I'm glad you asked that because that's a place where I'm so expert. You're going to think I'm really smart. You can design a three-wheel vehicle to have every bit the rollover resistance that a four-wheel vehicle does. But, and here's the big but, you must control the center of gravity. And with a four-wheel vehicle, you can have the center of gravity anywhere you want it to be. I'm talking about longitudinally between the wheels. You can load the rear end, you can load the front end, it doesn't matter. It doesn't affect the rollover threshold of the car. With a three-wheel car, you must put the center of gravity near the side-by-side wheel. Now, you can only put so much near the side-by-side wheels, right? I mean, physically, you can't put the whole car in between the side-by-side wheels. So you've got to stretch the center, you got to put it somewhere. End up with a center of gravity somewhere in here, It can't be in here. And you wouldn't want it anyway because then you wouldn't have any weight on your rear wheel. So the way you make a three-wheel vehicle have high resistance to overturn is you keep the center of gravity low, you bias it towards the side-by-side wheels, and what else? No, you keep it low. Oh, and you keep the side-by-side wheels wide. Now, on this vehicle, because the drive axles are right here, you can't move the driver ahead of those drive axles. Your feet are going to hit the axles. So you can't move the driver any farther forward. That means the weight of the driver is back here, which is a place where I don't want it to be, because it moves the center of gravity back. Well, if we had a front-end view of this car, and there is some on the website, this car has a 66-inch track. That's wider than my four-wheel car that I drive. And so that's how I made up for it. You know, there's only so low I can make the center of gravity. I can only get it so far forward. I put in a linear engine instead of a lateral front-wheel drive engine. And I even moved that engine as far forward as I could move it, you know. And I put the motor real low. The motor's real close to the ground back here. And, you know, I did everything I could do to help that car out. And what I really needed to do is move those front wheels farther apart. See, a three-wheel vehicle, if you draw a line from the center of this wheel to the center of that rear wheel, a three-wheel vehicle thinks that's the edge of the car. Do you know what I'm saying? So if you have the wheel out here, then, you know, it thinks that's the edge of the car, four-wheel vehicle. But when you draw a line here, it thinks that's the edge of the car, as far as overturn. You follow me? And so the only way you can get the edge of the car wider is to move this out to here. So if you move this out to here and you draw a line, then you've got, that line is farther away.
In simple terms, are you saying that that one is fairly stable?
Oh, yes. Yeah. It's got about a 1.2 G rollover threshold, which is about equal to your average family sedan. You know, it'll roll over. I happen to drive a Mustang, and the Mustang has one of the highest rollover threshold of any car. And I forget what it is, but it's something like 1.4 Gs or something like that. So it's not as good as my Mustang, but it's as good as your Mercedes or whatever. You know what I'm saying? It's in that range. So this car will slide before it overturns, is what I'm trying to tell you. And whenever I design a three-wheel car, I always shoot for 1 G rollover threshold. And what that means theoretically is the car will slide before it overturns. Because a passenger car tire has about a 0.8 G friction coefficient. Now, if you call Goodyear and you ask them, they probably won't tell you, you know. And there's stories around about, you know, sports cars cornering at 1.2 Gs. And I don't know how accurate that is. I mean, you can tilt the wheel and give it camber thrust. There's a few things you can do with suspension. But whatever you do, if you push that car sideways, the amount of force is limited by the friction coefficient of your tire. There's just no getting around it. Am I right, Howard?
Right.
You can't get more, you know, you can't resist sliding that tire sideways any more than the friction coefficient. And a passenger car tire has about a 0.8 G friction coefficient. You know, and so if you have a 1 G rollover threshold, it's going to slide before it turns over. And now that's a static. That's a static way, or what they call a rigid body way of looking at it. It's assuming there's no springs and there's no rebound and, you know, roll moments and all that sort of thing. You get a car into a dynamic situation where you're doing slalom turns, for instance, and the body is rolling from this extreme over to that extreme. Well, then that rigid body analysis no longer works. It doesn't hold up in real world dynamic kind of conditions. But from a static condition, that's what I do when I design three-wheelers, is I use static and I go for 1 G, at least a 1 G rollover threshold. And this car has about a 1.2 G rollover threshold. So that means it's going to slide before it rolls over. But I can turn my Mustang over, right? And all I got to do is put it into a skid and slide up against the curb, and then we'll roll over if I'm going fast enough. And yeah, trip it. And so will this, you know? So there's nothing you can do to make a car stay upright under all conditions. But under normal, out-of-control conditions, this car will slide before it overturns. Okay, did I bore everybody with that explanation?